So good morning, good afternoon, everyone. And I'd like to welcome you all. I'm Elizabeth Joseph, and I will be the host for this session on student perspectives in climate action. This is a very important topic. The shipping industry is a growing source of greenhouse gas emissions, contributing to climate change. And at the same time, we have the potential to reduce shipping emissions in a cost-effective and efficient way. So today we will be hearing from two excellent speakers and what actions can be done to reduce shipping's impact on climate change. It's great that these perspectives are coming from students. They are our future leaders in this field. So we have Sadi Rahman from the Bangladesh Marine Academy and Yegor Petrov from St. Petersburg State Marine Technical University. So just to note that throughout the presentations, you can send across your questions using Slido. And for today's session, it's #student, and we'll aim to answer these at the end of the presentations. So I'm now really pleased to introduce our first speaker. We have Sadi Rahman, a student at the Bangladesh Marine Academy. Sadia will be presenting all about hydrogen fuel cells as an alternative fuel for marine propulsion. Sadia completed his pre-sea training from Bangladesh Marine Academy in 2014 and worked as an engine cadet in shipping up until 2019. And he completed his Bachelor of Marine Science honours in December 2020. And he's also a promoter for environmental conservation and hopes for a better, brighter and cleaner future. So let's welcome Sadia Rahman. Thank you very much.
Hello, Elizabeth. Thank you for having me here. So I'm Sadi Rahman, and I'm here to show my presentation. I'm Sadi Rahman from Bangladesh Marine Academy, BSMRMU Bangladesh, and my presentation is regarding hydrogen fuel cell for marine propulsion. These are the contents that we'll be going through. At first, we'll be looking at the comparison of hydrogen with other fuels, then the classification of hydrogen storage, various types of hydrogen fuel cells, the implementation of those fuel cells on board ships, and finally, some advantages and disadvantages. Do you know that more than 9 billion metric tons of cargo transportation is done by ships annually? That's great because you can have whatever you want from the other part of the world within a few days or weeks, maybe, not so long. But this comes with a price, not just the price tag associated with that product, but international shipping accounts for 2 to 3% of global carbon dioxide emissions. What is this 2 or 3%, you might ask? In 2012, the industry produced over 960 million tons of carbon dioxide. Far more latest perspective is 2017, when international shipping was the 8th largest emission producer in the world. If you think about it, if international shipping were a country, it would be the 8th most producer of greenhouse gases. That is an amount that you cannot just scoff at. It's huge. We need to reduce it because according to Paris Agreement, reduction of fossil fuels is mandatory and alternative fuels should be used to reduce these emissions. Now we have one possible solution, which is hydrogen fuel cell. Here I have shown a basic layout of how this machine works. So you have hydrogen and oxygen, which combine together to create electricity. But how? We know the equation of how hydrogen and oxygen combine together to create water. We just split that into two. At first, hydrogen enters an anode, which is negatively charged. Here, the hydrogen splits into two parts. The hydrogen protons, they flow through an electrolyte. And the hydrogen electrons, they flow by this circuit. And in the cathode, we are running oxygen, which stays the same, but the hydrogen proton, which are passing by the electrolyte, and the electrons which went the other way, these three elements combine together at the cathode to create water. We know that the flow of electron is simply electricity. So by tricking the hydrogen electrons to take a different path, we are essentially producing electricity. And our byproduct is plain H2O, water. This is the comparison of energy content. We can see that we have diesel, a representative of fossil fuels, which has 45 megajoules per kilogram. It's decent, but alternative energy, natural gas, we can say LNG, it has higher energy content, 50 megajoule per kilogram. But hydrogen is the lord of them because it produces 142 megajoule per kilogram. According to various research, it might differ from 120 megajoule to 142, but that's not the fact. The fact is it produces more than twice, around thrice, the energy produced by other fuels. Now, the efficiency comparison. Hydrogen fuel cells at all percentage of rated load produce more efficiency than traditional diesel generators. Even at 100% working load, hydrogen fuels are far better than fossil fuels. Now the classification of hydrogen storage. We can store hydrogen basically either physically based or material based. In physical based, we have compressed gas or cold or cryo compressed gas or liquid hydrogen. In material based, we have adsorbent hydrogen, liquid organic hydrogen, interstitial hydride, complex hydride, and chemical hydrogen. To gain a better perspective, I have added some molecular bonds so that you understand. There are various types of hydrogen fuel cells, but amongst those, only a few will be necessary for marine propulsion. I'll be coming to that. The basic hydrogen fuel cell is PEM, that is proton exchange membrane. Now, if you see this layout, you can see that essentially the working principle of all the kinds of fuel cells are essentially the same. Only the electrolyte changes, the anode and cathode, the electrodes, those might change. And this is how the interclassification is done. That is why we name all the fuel cells by the electrolyte name. For example, as it has a proton exchange membrane, it is PMFC. When we use methanol as electrolyte, it is methanol FC. When we use alkaline, mainly potassium hydroxide, it is AFC. Phosphoric acid speaks for its name. Molten carbonate, we add here some carbonate salts. And in solid oxide, we add solid ceramic as the electrolyte. And these have varying operating temperatures, which will come into play when we get more into it. This is the basic layout of all fuel cells. You can say that this is the fundamental one, that is PEM. It is the leading fuel cell type for passenger car application. Toyota Mirai has already implemented it in land-based use. It uses a polymer membrane as the electrolyte where the hydrogen ions pass through. It operates around a relatively low temperature, 80 degrees Celsius, so it's quite warm. However, this system is very sensitive to fuel impurities, so you have to make sure that you always give pure hydrogen in the anode side. Now we have molten carbonate fuel cell. These are more flexible because as we add carbonate salts inside the electrolyte, it needs to be heated to around 650 degrees Celsius. In this temperature, the salts melt down and they release carbonate ions, which further facilitate the reaction. However, this reaction is not totally emission-free like PEM. It produces some amounts of carbon dioxide. However, it's far cleaner than the fossil fuels that we have. In solid oxide fuel cell, the ceramic electrolyte, it is non-porous in nature. However, it is porous enough to let the hydrogen protons pass through. It can reach 60% or even higher levels of efficiency. But this operates at a staggering 1000 degrees Celsius or nearby. This is a system which is very effective for large scale applications like industrial power generation and our main issue, onboard ship. Now, I showed several types of fuel cell types. Amongst them, I discussed only three. You might ask, why these three only? Because these three are the most effective ones to be used on board ship. We know that hydrogen is good, but how to use it? Let's have a look. This is the basic layout by the basic hydrogen fuel module, that is PMFC module. Here we have three basic parts: the hydrogen storage, the fuel cell module, and the stack. And additionally, we have a heat exchanger. So hydrogen storage contains liquid hydrogen that passes through a regulator and goes to the anode side. As sea air has lots of salt in it, sodium chloride, magnesium chloride, and whatnot. It's not very good for this system. So we need it to pass through a filter. Then we force the air by a blower, and we sprinkle some water spray in the humidifier section. It makes the air optimal for conducting the operation. In the stack, the hydrogen and the air, which has oxygen, does its thing, and we get electricity. And as a byproduct, the water is created, which we vent out by the water separator. We have a purging valve here to increase the efficiency of this system. And we have added a heat exchanger because, as we told earlier, PEMs are very susceptible to temperature change. So we need to maintain it at an optimum temperature. That's why we add the water pump, tank, and the exchanger system. In molten carbonate fuel cell modules, we can see that the working principle is the same, but it has some added parts. As it uses carbonate as the electrolyte, we can use other fuels rather than hydrogen, namely natural gas or methanol. You just blow it through a fuel or steam heater. It goes to a reforming chamber. From that, it goes to anode, but some of it goes to a catalytic combustion burner. We have our air, which is blown by a blower to that same catalytic combustion burner. It goes to the cathode, and in the stack, in the fuel cell stack, we have our reaction, which produces electricity. However, here the cathode and anode, they produce lots of carbon dioxide and heat. We take this as an exhaust and we flow it through a evaporator. This evaporator further facilitates the reforming of our initial fuel, and finally it is exhausted. However, this does release some carbon dioxide. But in the grand scheme of things, this is a module which we can already use with the existing fuel we have. This is essentially the same system with direct control. Here we have added an auxiliary fuel line, another catalytic combustion burner, and a turbine added with compressor. The fuel goes by the main fuel. It goes to a recuperator, which is essentially doing the heating stuff. It goes to the reforming, goes to the catalytic combustion burner. We blow air by the compressor. It is compressed, so we can add more air. It goes by the combustion burner 1. It goes to the cathode. and we have a reaction, we get electricity. However, this system does not have enough temperature to run a gas turbine. So we add an auxiliary fuel. It goes to a catalytic combustion burner 2, and the exhaust that we get from cathode, we blow that to that same catalytic combustion burner 2. There, the energy and the heat, the temperature that we get, we simply pass it to the turbine, which further creates more electricity. And we have the evaporator, which does the reforming job easy. And finally, we let out the exhaust. This is the third system, the third module type, that is solid oxide fuel cell module. Here, the fuel enters a fuel preheater because we need so high temperature. After that, we send it to reforming and it enters the anode. We have our old air, we send it to a air preheater, which then enters the cathode. In the stack, we have the same reaction, we get electricity, and all the exhaust from anode and cathode go to a catalytic combustion burner. It further facilitates the air preheating, the fuel preheating, and for added bonus, we have added waste heat recovery system here in the form of an economizer. So we get more energy. Finally, we let out the exhaust. And our last module, last schematic diagram, is the direct hybrid SOFC system, where we have used not only the gas turbine system, but also the economizer, and we've combined it as a whole. Here we have our fuel doing the preheating, going to reforming, going to anode. Our air, which is further compressed, more air, more energy, it goes to cathode, we get our electricity, it enters the catalytic combustion burner. So we have a high temperature exhaust ready. It not only runs our turbine, gives us energy, it does the heating, preheating, and finally it goes also in the economizer, waste heat recovery. So we get 3 forms of energy from this system. Now, all the modules that I have shown, this might seem theoretical, but actually these have been already implemented in various ships around the world. We have FCS Alsterwasser, is the first passenger ship powered by HFC, maximum power up to 100 kilowatt. It's 25 meters long, designed to accommodate up to 100 passengers, maximum speed up to 8 knots. The power system has 12 storage tanks with 50 kilogram of hydrogen each at a pressure of 350 bar. 2 PMFC modules of 48 kilowatt are running here. 7 lead gel battery packs are added with total capacities of 234 kilowatt hour and total voltage of 560 volt, a 100 kilowatt propulsion electric motor, and the 20 kilowatt bow thruster. The hydrogen storeboard can allow the ship to operate for 2 or 3 days without any refueling. But it takes only 12 minutes to fill up the entire hydrogen storage tanks. We have Nemo H2. It's a PMFC power system, that is the basic one, developed for Nemo H2. It's 22 meters long. It can accommodate 88 passengers at a speed of 8.6 knots. The power system has 6 storage tanks with 24 kilograms of hydrogen at a pressure of 350 bar, 2 PMFC modules of 30 kilowatt, 55 lead acid battery packs with total capacity of 70 kilowatt hour, 75 kilowatt propulsion electric motor, and 11 kilowatt bow thruster. This system was used to power the propulsion motor directly or charge the lead acid battery packs. It can be used as a backup option or alternative. The refueling process happens once a day. SF Breeze was a concept hydrogen-powered passenger ferry. It's developed to accommodate 150 passengers at a maximum speed of 35 knots. The power system consists of single Type C pressurized vessel. The storage tank on top deck with 1200 kilogram of liquid hydrogen, 41 120 kilowatt PMFC modules containing 4 PMFC stacks, each of 30 kilowatt, and 2 water jet propulsion systems driven by AC motors with a power of 2000 kilowatt each. No additional battery packs are installed, and the endurance was up to 100 nautical miles. Finally, we have Viking Lady. It's an offshore supply vessel, so it's not a passenger carrier. It utilizes fully electric propulsion powered by dual fuel engines. It's the first ship using a molten carbonate fuel cell power system as APU. The MCFC module delivered a DC voltage varying between 380 to 520 volts, depending on its load condition and age. The electrical system had been designed to compensate for the slow response of the fuel cells, because at sea, at times the conditions can get rough. So to maintain with the dynamic load changes, it would protect the lifetime of fuel cells from diminishing. The ship operates at low loads during maneuvering or berthing, but the methane slip from LNG fuels engines are also considered, which would reduce emissions, noise, and vibrations. Now that we have discussed about the examples of these ships, I have a few recommendations. The scientific research for new procedures need to be encouraged, because the more we research, the more we can find what are the alternative ways that we can improve this technology. New materials are needed to increase the efficiency. The electrode, which is used basically platinum. Platinum is not cheap. It's one of the most expensive materials in the world. So we need new materials, both as electrode and as electrolyte. We need to increase hydrogen production, because our methods of hydrogen production may not be sufficient enough yet to sustain a hydrogen-based economy. We need cheaper hydrogen price with cheaper components, which is a result of the economy. The government should introduce incentive schemes. That means people who use hydrogen fuel related accessories or engines, they need to have incentives provided from the government. And finally, we need to increase the supply infrastructure of hydrogen. Ships rely on bunkering of their fuels. We need to provide the ships with constant hydrogen supply. It does not mean that a ship needs to produce, but there has to be ample scope of bunkering hydrogen. The advantages of hydrogen fuel cells over other engines are: it completely reduces or eliminates greenhouse emissions. It has superior efficiency at various loads of the system. With high temperature fuel cells, we have potential of heat generation. As there are no moving parts, the system is basically, it's so easy to maintain. And for the same lack of moving parts, the noise and vibrations are also reduced. And you can have lots of flexibility in the installation and operation based on your load. However, hydrogen does come with a few disadvantages, mainly expensive technology. The hydrogen fuel cell stacks cost a lot. The platinum electrode costs a lot. Electrolytes cost a lot. The supply infrastructure, which is very low, it's also costly. We need to teach personnel to be accustomed to this new type of technology. It doesn't happen in a day, so it's also expensive. Also, we have existing ships which rely on fossil fuels, so we need to convert them. Overall, it's an expensive technology. And finally, hydrogen is very flammable. That 142 megajoule of energy does not come from nothing. It's very flammable, and that's why the storage of hydrogen is also an issue. However, there are some disadvantages, but if we weigh these with the advantages, we see that the advantages are far more. I strongly implore you to consider hydrogen fuel cell as a potential for marine propulsion, not just in the future, but starting from our present. Thank you.
Brilliant. Thank you, Sergio, for that interesting presentation. I've certainly learnt a lot more about hydrogen, so thank you. And now moving on, I'd like to introduce our second speaker, Yegor Petrov. He's a student at the St. Petersburg State Marine Technical University. Yegor is from Russia, and since childhood, he's always been interested in the maritime field and has always wanted to be a marine engineer. So he will be today presenting on the opportunities for ships to use wind power and whether wind power can compete with ships using traditional engines and other green innovations. So let's welcome Yegor Petrov. Thank you.
Thank you too. First, I want to thank Institute of Marine Engineering, Science and Technology for opportunity to participate in this conference. My name is Yegor Petrov, and I'm student of St. Petersburg State Marine Technical University, which is located in Russia. And I'm going to discuss a topic, wind propulsion in modern shipbuilding. First, let's take a look on the table of contents. The first, we will have a little introduction. After this, we go to the brief history of wind-powered ships, then discuss advantages and possibilities of this technology, and then go to the barriers. So, one of the most important global problem in our time is global warming, and the mechanism of global warming is greenhouse effect. And one of the most important greenhouse gas is carbon dioxide. As we can see from these figures, here we see that marine consists of 20% of all carbon dioxide emissions in the United States. So if we see the global statistic, we can see that most big amount of carbon emissions is related to containers, bulk carriers, oil tanker, chemical tankers, and other transport vessels. This is very important because we can just solve problem to take out these vessels because they're very important for our economy and for our way of life. So here are some statistic that said that we've got a lot of producing carbon dioxide in marine industry, and not only carbon dioxide, of course, we've got the COX gas and NOx gas too. These gases also take a big harm to the planet and to their nature. We can have a couple of decisions how to change this way of things. One of the decisions is to change the propulsion system from the diesel to others. And one of these decisions is, of course, usage of alternative energy sources. For example, it can be solar or wind. I choose wind power for my little research, and I will show you how it works. The first brief history. As you know, humanity used wind to propulsion for centuries, from the ancient times to the 19th century. But when after um, diesel engine was introduced in the late 19th century, the alternative engines did not were not used by countries, companies, and all humanity at all. So um, uh, in the second half of the 20th century, we can see the increasing of amounts of the projects which are dedicated to the alternative sources of energy and also the wind power ships. For example, we can see it here. Why we have to use the wind power ships? Um, at first, I will give you a short look about the advantages and possibilities of using this technology, and then I will discuss them closer. So the first is the high speed and high sea because of wind speed. We can use Earth global energy. We get a great possibility of fuel savings, of course, decarbonization role, and also we have the highest energy efficiency on low speed. The first two topics, the high speed and usage of Earth's global energy. As you can see, we have two maps here. The left one shows us the annual wind speed in the different parts of the Earth. And the second map shows us the most important trade routes in oceans and seas. So, as we can see, they are the same in most ways. So it can say to us that we can use the power of wind to deliver our cargo without any problems, because the winds are the constants of our Earth. So here the two researchers which give us the picture of possible fuel savings. As we see here, that the different types of wind engines, for example, flanter, wing sail, give us a fuel savings from the 16% to the 20, 13 or something like that. If we go to more concrete numbers, we see that we can save probably 30 thousands of kilowatt hour for the market from the Europe to Brazil. The next part is decarbonization role and energy efficiency. The shipping sector is projected to contribute more than 6% of global greenhouse emissions by 2050. Wind propulsion could cut emissions by more than 10%. As I say, we've got a great save of fuel from 24% for a single flat rotor, 1 to 32% for a towing kite, and up to 25% for the eco-wind sails. And of course, some estimate savings from 10 to 60% at low speeds. Wind propulsion also is most effective at slower speeds less than 16 knots and on smaller ships. So we can say that the wind power ships can be more effective if they have a small size and they also have a low speed. So we discuss advantages and possibilities. So we can go to the barriers. I divide them into the three groups. The first is economical. The second is organizational problem or foundation problem, and the behavior problem. So the first and the one of the most important economical problem is the valley of death. So what is this? As you know, the company's success is closely interconnected with this cash flow. And clearly that the young companies on the first period of their existence need resources for development. We can see it from the phase one when we see that the cash flow is above zero. So they don't have the free money to improve their technology and their business. And with that, we have a contradiction. So to increase cash flow, we need to develop company, but we don't have enough cash flow fundamented. And as it often happens, companies can't solve this contradiction and die. As we can see from the figure, the most difficult phase of company activity is phase two, when they need the further investment. And if company management can't find it, company have to stop its activities. As we can see from the result of the THIX company research, only one of THIX company successfully go through the valley of death. And this is not good statistic. So it shows us that the commercial efficiency of these projects is not very high. So the next important thing that we have to discuss is the price of the kilowatt of energy depending on the type of the fuel. As you can see from table, we see that wind energy is one of the most expensive. The most expensive is only solar energy from the photovoltaic or the thermoelectric ways to get it. But of course, it's characteristic for all alternative sources of energy. But nowadays, there is a tendency to in value of alternative energy kilowatt cost. The next problem also go from the statistic researches. We see that oil price development and temporal event pattern. As you can see from figures, that is strong correlation between oil price and number of projects in wind power ships projects. So when the price of oil is low, we have a small amount of events because of the market reasons. The companies don't want to change their politics because they have enough money to build ships and use the diesel fuel. But in the periods of high price of oil, we see increasing of these events. we can make a conclusion about strong dependence of wind propulsion projects to the oil market. So if the price of oil will increase, we will see a lot of projects and a lot of ships of these types. So if we don't see this, we will see the small amounts of this kind of ships. The next thing is market. We can see on figures with distribution of market shares by type of a propulsion system. According to the graph, the market of global marine propulsion engines is growing year by year. But the part of wind and solar propulsion is still the same. Is the red part of the diagram, and we see that it's the same from the year to year. Also, United States statistic give us picture of little influence of wind propulsion on market, and that means that capital investments in this area are not growing. And as we see from previous topics, the shortage of further investments is the main reason of company closing. So if we don't have part of market, we don't have investments, and our company have to end its development and its life. The next problem lies in the area of constructive problems. As we see from figure, a rapid growth over propulsion system size, increasing its ship size. It's obviously, but it is also very important because it's not the linear, but the parabolic division. This is effects on material consumption, and in connection with this, ecological and economical aspects of projects. The next is the behavior barrier. We can discuss the objective problems of development, which are connected with the objective problems. We also have such problems which are connected with the human nature and human psychology, and it is a behavior barrier. As we see, conservatism and fear of change lead to interior which can only be overcome by educating actors with the shipping industry and creating curiosity of the technology. Nobody is going to buy the things without understanding completely how they operate and how they function. If the product works, people buy it, and etc. It's this from the interview of one of the ship owners, which were taken in the 2013. It's almost 8 years ago. So also there is a financing problems, and we see that the most important donors of the international organizations, United States of America, United Kingdom, and Japan, give a small amount to the international organizations, to the International Maritime Organization. If we don't have enough money, we can provide our projects and change the industry. In conclusion, I can say that wind power ships, this technology which we can use on the not on the high speed or on the um, big size ship. We can use it in small ships and small and in the low speeds. And it's the place of these projects. And for the big ships, big cargos, we have to use another technologies. Also we can see that there are different barriers, and the one of the most important, of course, is behavior. And we can change it from the changing policy for the some system of donation to the organizations which have worked in green marine industry. The most important thing we have to remember that our planet is on the first place, and we have to save it. So thank for your attention.
Brilliant. Thank you, Yega, for that interesting presentation. Really good. So I'd now like to move on to the Q&A. And just a gentle reminder for everyone on the call that we're using Slido. And for this session, it's #student, where you can write in your questions. So the first question I have is directed at Sadi. So what is the current state of use of hydrogen fuel, and has it been introduced in ship operations? If not, in how many years it would be available? If you want to share your video. And
Yeah. Am I audible and visible?
yeah, can see and hear you.
Okay, thank you. Well, the current state of hydrogen, it's very much in the preliminary stages. There are only a few vessels that have introduced the hydrogen fuel cell system in their running operations. It's mainly because there are some challenges that we still have to face. So it's still in a very beginning stage. However, as the Paris Agreement dictates, we have to curb our emissions within 2050. So as the years proceed, we are proceeding towards a far more greener future for hydrogen. The biggest one of the if not, it is the biggest ship industry in the world, Maersk. And Maersk has already started investing in hydrogen economy. And with the leaders paving the way, others are soon to follow.
Great, thanks for that. Yeah, there's a bit of a follow-on with that, where the question is, what challenges do you think that the shipping industry will need to overcome to be able to introduce hydrogen more widely?
Well, there are lots of challenges right now, because the shipping industry, it's basically global trade, and is trade is dependent on profit. You don't get profit if you run an expensive fuel. You need to maintain the balance between profit and energy efficiency and maintaining the environment. You see, 2020 sulfur cap regulation, ship companies did not start from goodwill to curb their sulfur emissions. It was mandated by the IMO. Without mandation, they would not have done it. So there are lots of challenges, and the infrastructure is an issue. But I believe if IMO makes the regulations more stringent, the companies would have no other way rather than not only accept hydrogen. We have solar, wind energy, as my compatriot here, Yegor, has said, and there are other alternative fuels are being studied. So I think these are going to be the future.
Great, thanks for that. So I've now got a question for Yegor. Where did it go? All the questions are being there was one on wind power, and there's lots of questions, and let me just see. Yeah, so are you aware of shipping companies that currently use wind propulsion, and is there a proof of concept that can be promoted?
Of course, There are different concepts of these ships. The one of them I show in my presentation when I speak about brief history. And also during the conference, we have presentations from the companies which provides the wind energy and the workable projects of this technology.
Great, thank you. So another question is, this is to Sadi, how do you think hydrogen compares to other alternative fuel options for ships, such as biofuels?
Well, I have showed one slide in my presentation where hydrogen is it's not nearly, it's more than twice. It produces more than twice energy of liquid nitrogen gas. And methanol, ethanol, biofuel, biomass, we have Brazil producing cassava, and that all those things. Hydrogen has far more energy efficiency than all alternative fuels that are being used so far. The only issue is that hydrogen is a bit pricey.
Cool, thank you for that one. So I've got another one just going back and forth on the wind propulsion. Back to you, Jaeger. So wind propulsion is quite traditional. Do you think there are new research areas that could help to improve its efficiency?
Of course, because we can see that, for example, sails, the simple, they nowadays can also make from metal, for example, and flattened rotors and some turbines, of course, improve the efficiency of wind propulsion.
That's great, thank you. So looking through the questions, so back to hydrogen. So I've got one. Would hydrogen be able to power an entire vessel, or would there need to be other fuel sources for longer journeys?
Okay, this question, the answer depends on the type of the ship that we're using. You see, hydrogen ships that are being used currently are mostly passenger ships that have low loads. But if we increase the load, hydrogen might suffer in the long run, because hydrogen fuel, the problem is not with the hydrogen production. Hydrogen fuels are more than capable enough to produce the power necessary. The problem relies in the bunkering infrastructure. You see, you can move from point A to B. You can go on a North Atlantic voyage, but the thing is, you cannot refuel in the midst of the sea, whereas traditional fuels have lots of bunkering options. That is why hydrogen fuels are being used mostly in low distance, that is a small distance, and passenger ships. However, there are some ships being developed which are cargo carriers, which have used hydrogen as alternative power unit, auxiliary power unit, so my bad, that is APU. It's not powering the entire ship, but it is significantly reducing the carbon dioxide emission, and it's also helping the companies to get their desired profit as the economy is being saved due to less fuel consumption.
That's great, thanks. And just to lead on to that question, would you be able to share a little bit more about the differences across countries for their possible implementation of hydrogen? What could be the challenges?
Well, right off the bat, Norway and Japan comes to my mind, because these countries have already started to completely revitalize their entire economy. They have made a plan to gain hydrogen-based economy in the coming years, Norway and Japan. And other Western European countries such as Denmark, then we have Ireland, even UK has lots of research regarding hydrogen fuel. I can name Canada. That is the mostly the countries based on on the NATO region, the North Atlantic region. They're investing heavily in hydrogen fuel. And we have South Korea, Japan. In the Asian side, who are investing in this sector. Also, India has been progressing towards hydrogen-based terrestrial vehicles. So they're also proceeding in this economy. And the main problem regarding hydrogen is the infrastructure. As the more countries implement hydrogen economy in their infrastructure, hydrogen is going to get a better chance. You see, Tesla did not get Tesla electric motors. They did not get their infrastructure in a day. In the USA, there were lots of electric stations already around the country. Those stations produced enough energy, which became the hub for the powering the Tesla engines. If we can do the same for the seas, hydrogen is a very high reality.
That's great, thank you. So now moving over to Jaeger, I've got a question around the courses and also for you, Sadi, as well. It's about the courses that you're studying at college, university. Is there training that you've received on alternative fuels and decarbonisation? So we'll start with you, Jaeger.
We don't have the special decarbonization course, but we have the ecology, maybe in 2 years, as I remember. And of course, we studied the new types of engines, fuels, and all materials. And of course, we discuss the question of ecology on these fields.
Great, thank you. Over to you, Sadi.
Well, as I studied from Bangladesh Main Academy, I should say that I'm privileged to have such a great course regarding energy efficiency. We have a few credits regarding this. We learned how to operate our ships more efficiently with less energy consumption and more optimization of the fuels. So our basics started from our academy, and when we were affiliated with Bangabandhu Sheikh Mujibur Rahman Maritime University, BSMRMU, our knowledge became further solidified. My passion for hydrogen fuel, my passion for alternative energy, renewable energy, started from my academy and my uni. Thank you.
That's great, thank you. So back over to you, Jaeger. So you mentioned that people will not buy things if they don't understand how they work. Do you think that there is a lack of understanding for the potential of wind?
Of course, the potential wind is very high, and I think we can use the conference like this to show people how they works. And also, as I said, that IMIL also can take a part in this. If they will make the study materials for the wide scale of people.
That's great, thank you. Now back over to you, Sadi. So a question from Jeff. So what do you anticipate the volume is required for hydrogen storage compared to existing fuels? And do you think we will overcome the safety risks of storage?
Okay, well, I showed a slide where I demonstrated various kinds of hydrogen storage. You see, hydrogen is the simplest element in the universe. It is the lightest gas. You can compress it as much as you want, and you can have lots of storage for many people have this issue. Many people worry about this, that hydrogen tanks will be so large, we cannot carry enough cargo. It's not the case. As it's a gas, you can compress it. It will take very less space. And I personally prefer the liquid hydrogen storage, because when you liquefy it, and it's definitely compressed, and it takes less space. And It's the difference between carrying a fossil fuel and hydrogen fuel in a liquid state or compressed state is not much on the effect of it is not much on the overall efficiency of carrying the cargo, which is the main concern here. As hydrogen is so light, you don't even have to calculate the trim and others. You have to calculate the trim to keep your ship stable, but with other fuel, liquid fuel, you need to calculate it more. But hydrogen gives you much more leniency. And there was a follow-up to that question, I believe.
Yeah, so the follow-up is, how do you think that we will overcome the safety risks of the storage of hydrogen?
Yeah, safety storage of hydrogen, it is an issue because many of us know about the Hindenburg tragedy that happened during the 20th century. A large balloon filled with hydrogen gas blew up. So many people are paranoid about hydrogen. But the thing is, that was the basic cause why intercontinental travel with the air balloons stopped, because hydrogen was so flammable. But but the technology that we have, and as I mentioned, that hydrogen is so light, if you puncture a hydrogen container, the hydrogen would go out so fast that even if you hold a flame to that hole, it would not ignite. Rather, it would be pushed away due to the sheer pressure of that hydrogen wanting to be released into the air. So yes, safety issues are a concern, but with robust material which can provide for ample safety and ample storage to the hydrogen container, we can easily eliminate this issue.
Okay, great, thank you. So now this is kind of a question open to both of you. So we'll start with Diego. Where do you think support needs to come from to introduce these solutions? So in your case for wind power, is it up to the shipping companies, the governments, or others?
Um, mm, it's a good question. Of course, the most important is government, because the states have the most strong institutes. They can use not only brutal force, taxes, maybe some laws, but also they can support and help in other ways. What if we talk about the shipping companies? They can use their profit to open courses, universities to train people, of course, and also the simple people can help. They can just join some societies and improve the knowledge about the alternative energy technologies.
Great, thank you. And Sadi, from the hydrogen perspective, where do you think support needs to come from to introduce these solutions?
I believe the first support needs to come from IMO, International Maritime Organization, because prior to 2020, no company in the world, none of them bothered to reduce their sulfur emission because it was not needed. IMO needs to give regulations first. Then the shipping companies, in order to stay in the business, they will implement those later. So IMO needs to provide the first framework. About governments, I believe that, well, Paris Agreement, which wants us to be in the, which wants us to have less global warming, to be our temperatures to be around the pre-industrial levels. There are two leading economies of the world have not yet signed that because they don't want it. They want their economy first. They are not worried about the environment first. They want economy first. So governments are going to be nuanced. They are not going to immediately accept it or reject it. The basic issue needs to be the economy. There has to be profit. If the government sees that by implementing hydrogen, you can have profit, then they will do it. And I believe the way to that would be if IMarEST, my bad, I meant IMO, if IMO starts fining ships which do not follow its regulations. As the regulations become more stringent, the breaking the rules will have dire consequences. Then the countries and the companies, all of them will say that, hey, this is not effective. We are losing money. We need to switch to this economy. Whatever this is, we need to do it in order to stay in the business. So first step has to be taken by IMO.
Okay, that's great, thank you. And just had a question around carbon CO2 from the hydrogen systems that you've mentioned. Are there what are the other CO2 quantities compared to the current marine engines based on hydrogen as a marine fuel?
Could you repeat that question again?
Yeah, so sorry, I'll rephrase it. So you mentioned that some of the hydrogen systems can release some carbon dioxide. What are these CO2 quantities and how does this compare to current marine engines?
Okay, thank you. Well, some of the hydrogen fuel cells, namely molten carbonate fuel cell and solid oxide fuel cell, they release some quantities of carbon dioxide, because inside the system, not only we are using electrolytes carbon dioxide, carbon monoxide also, but also in the anode and also in the cathode, we are introducing carbon dioxide in the cathode as a direct gas, and in the anode we are introducing other fuels such as LNG and methanol. So yes, there are some carbon dioxide emissions, but if you compare it with other traditional fossil fuels, the percentage is very meager. You have an engine which runs on a total hydrocarbon based system, a fossil fuel. Let it be LNG, let it be diesel, heavy fuel oil, or LSMGO, whatever it is. The carbon dioxide emission is going to be always very high. Compared to that, it would be only a few percentages. But it depends on the context of which system are we using, and also the which fuel are we using. The percentage of carbon in that fuel, how does it interact with the oxygen, and how the carbon and oxygen produce carbon dioxide. As a student, it's hard for me to calculate exact figures, but that is the basic idea that I can give you.
No, that's great, thank you. So moving over to Jaeger, we've got, you've talked, and actually to both Sadi as well, but I'll hand it over to Jaeger first. You both talked about the importance of addressing climate change and how much of a role and the question is, how much of a role can the marine and shipping sector play to address climate change? And a follow-on with that question is, did this attract you to work in this industry?
The first half of the question, the answer that me and Sadi give, we have basically numbers, but of course we have to mention that the lungs of our planet is ocean. Because the plankton is about, I can make a mistake, but 19% of the circulation of oxygen in atmosphere is made in ocean. And because of it, ocean is very important. And if we want to have our planet healthy, we have to take a look on the ocean and seas. The second half is about, can you repeat, please?
Sure. Yeah, the second part was addressing climate change. Is that one of the reasons why it attracted you to work in the industry or study marine engineering?
Yes, of course. And also, I was born in a city where there are a lot of marine traditions, and my family also take part in this industry. So, um, uh, if I if I didn't choose the marine, maybe I can fight against climate changes in other fields. It's not necessary to only to the marine. But the mostly is the tradition for me, marine industry.
That's great. Thank you for that. And Sadi, yeah, for you, how much of a role do you think the marine and shipping sector can play to address climate change?
Well, the marine and shipping sector, that is the international shipping sector, said it in my introduction that it is the in by the statistics of 2017, it is the eighth largest producer of greenhouse emissions. Just imagine a country which is the number eight in destroying the environment. That is where the marines. That is where the international shipping stands at right now. It's We don't want it to be here. We take the credit for running the entire globe's economy. More than 80%, it should be around 90% by now. More than 80%, 90% economy of the world is based on international shipping. So we have a big, huge role. If only this role could be furthered to save the environment. I know IMO has already started taking notice of it, and many major companies of the world have already started abating their emissions. But if we do it faster, we can save the world faster.
Yeah, and to follow on with that question, can you share? Was that one of the reasons that attracted you to this industry, or is there any other reasons as well?
Well, my hometown is Chittagong in Bangladesh. It is a renowned port city, which has been operating for more than 500 years right now. So, growing up in this city where I have where I have the Bay of Bengal in front of me and hills behind me, since my childhood, I have had always this dream to venture out into the open blue seas. And being in ship for more than 1 year, I've seen some views, I've seen some sights that can never be seen from the land. These are the things that attracted me towards the ship, towards the sea. But when I started sailing, I saw that the emission the emission that was coming from my ship, it doesn't look so clean. It's not good for my environment. All of this factored together not only drove me towards marine, but also drove me towards climate change and taking action against it.
That's great. Thank you. So great to hear the passion to fight climate change. Thank you, Yega and Sadi. And I have there's one last question coming up, unless there's any more that do come through. But it's what questions would you want to ask shipping companies about these issues? So either one, Yega, yep, go
Maybe
ahead.
okay. So the first of all, we all understand that the most important thing for every company is profit. And we have to work with it. The first, maybe it's not a question, but if you can put the profit on the first place, you can make a crime. And climate change and what some companies do with the environment is a crime, ecological crime. And we have to fight against criminals because we live in society. A company have a lot of different ways to have a profit. not only to destroy our environment. So the SETI told about that, and I told that there are a lot of different opportunities also to gain profit from the cargo, not only cargo, from passenger and other. We have to change policy, and we have to use different methods to improve the ecological side of our life.
That's great. Thank you for that. And Sadi, any questions that you would like to ask shipping companies?
Yeah, I have a little question for them. That is, what is shipping companies and all the trade that goes around the world? It's we know how it works, why it works. We understand. My question is, what are we going to do with the economy if the year we live in we cannot breathe? What are we going to do with property if our children don't have enough land because the seas are rising due to global warming, and we don't have any we won't have any land to stand? Being from Bangladesh, I'm in a country which is very susceptible to the global warming and sea level rise. I don't know whether my children, if I have someday soon, I don't know whether they would get this land or not. My question to them is, do you think hydrogen, biodiesel, wind, solar, all these alternative energies, do you think are this feasible? And if you think are this feasible or not, I have a follow-up question to the companies. It's not feasible. The question is whether they're feasible or not. The question should be, when are you going to use it? We know they are feasible. We need them not for future, not after 2050. We need them to be implemented right now. As Diego have shown, the wind energy, as I have shown, hydrogen fuel cells, wind energy rotors, they need to be implemented on ships right now. Hydrogen fuel cell stacks need to be implemented on ships right now. Please do not think about feasibility. Just, I would like to ask them, when and how are they going to implement it on their ships?
Great, thank you. Very powerful stuff. And I think that really summarizes the theme of this session, which is climate action and making that change. So thank you, Jaeger and Sadi. Really great presentations and great Q&A at the end. I mean, I've learnt a lot. There's been really good insights. Thank you for this discussion and all the opportunities that we can make changes now to help the shipping industry reduce its impact on climate change and help society. So I'd also like to thank the delegates who have dialed in to this session, and thank you for your questions. The conversation, however, doesn't stop here. If you've experienced other sessions within the conference, we do have a networking session which you can dial into now on the Wonder app. And then we also have later on, I think in the next 30 minutes, there's also going to be some closing remarks from the IMarEST conference. So anyway, thank you once again, Jaeger and Sadi. I wish you all the best with your future studies and careers, and do hope to see you around leading the shipping and maritime industry. So thanks everyone, and I hope you all enjoyed the conference. Thank you.